Welcome to Hired in ET. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. You've tightened your Azure spending, right-sized your virtual machines, and committed to reserved capacity. Then someone on the team creates a temporary jump server for a weekend project and adds a network security group rule allowing RDP on port 3389 from the entire internet. The project ends, but the rule stays. Within hours, automated scanners discover the exposed port and begin testing usernames and passwords. Most attempts fail, but the server now receives thousands of login attempts every day. If one account uses a weak or reused password, that forgotten rule could become the attacker's entry point. From there, the attacker may attempt to disable security tools, steal credentials, move to other systems, or encrypt data. Defense in depth exists because people make mistakes. One forgotten network rule should not be enough to compromise an entire environment. In this lesson, we'll reduce that risk using just-in-time access, Microsoft Entra authentication, modern disk encryption controls, Defender for servers, vulnerability management, anti-malware protection, and automated patching. By the time you finish this part, you'll walk away with 3 concrete abilities. 1. Lock down management ports using just-in-time access so RDP and SSH stay closed until you, and only you, open them. 2. Ditch static SSH keys and local passwords. Your VMs will leverage Microsoft Entra ID, formerly Azure AD, for authentication, removing the risk of leaked credentials. 3. Encrypt every disk using the method that actually fits your workload, and enable Defender for Cloud so you're constantly scanning for CVEs and missing patches. No theory, no fluffy overviews, just the exact steps you'll take in your own subscription. Azure's Defense in Depth model stacks multiple layers, from the physical data center up to your application code and data. The exact split of responsibilities can vary by service type, but broadly, the underlying physical infrastructure is managed by the cloud provider, while layers like identity, network, compute, application, and data tend to fall under your own control. Today, we're zooming in on the compute layer, the controls you can bolt directly onto your virtual machines. If the identity and network layers get breached, your VM hardening is the last stand before an attacker reaches your data. So we're going to lock that layer down tight. Picture a developer who connects to a staging Linux VM once a week. Because the developer's home IP address changes, someone creates an NSG rule allowing SSH on port 22 from any internet address. That decision is convenient, but it leaves the management port exposed every hour of every day. Automated scanners continuously search the internet for open SSH and RDP ports. Once they find one, they can test common usernames, leaked passwords, previously stolen SSH keys, and known vulnerabilities in the exposed service. Just-in-time VM access changes that model. Instead of leaving the management port open continuously, JIT keeps access restricted until an authorized administrator requests it. The request is limited to an approved source address, selected port, and short access window. When the window expires, the temporary access is removed automatically. JIT does not replace strong authentication or proper network design, but it dramatically reduces the time during which a management port is reachable. Here's what happens when you use just-in-time VM access. Step 1. An administrator requests access to a protected management port, such as port 22 for SSH or port 3389 for RDP. Step 2. Defender for Cloud verifies that the administrator has permission to request access. The request specifies the source IP address, destination port, protocol, and requested duration. Step 3. Defender for Cloud temporarily modifies the applicable network control, such as a network security group or supported firewall configuration, so the approved source address can reach that port. Step 4. The administrator connects to the VM during the approved access window. Step 5. When the window expires, Defender for Cloud removes the temporary access automatically. One important warning: JIT cannot protect a port if another higher priority NSG rule already allows that traffic. Always review the complete NSG rule set and confirm that a broad allow rule is not overriding the protection you expect JIT to provide. Quick recall: we just walked through the JIT loop. When your predefined access window ends, what happens automatically without any manual cleanup? The biggest mistake beginners make. They enable JIT on RDP and SSH and think the VM is bulletproof, but their application port, say 80 or 443, might still be listening to the entire internet. If a web app gets exploited, the attacker can pivot laterally from the compromised web server to the database subnet. No JIT needed. A pro layers JIT on top of strict NSG rules. Web ports only accept traffic from a load balancer or a specific external IP. Application security groups separate tiers, and every inbound rule is scoped to exactly the sources that need it. JIT closes the management door, but network segmentation makes sure an attacker can't walk from one room to another once they're in. JIT can be configured through the Azure Portal, PowerShell, the Azure CLI, or the Azure REST API. When you automate it through the REST API, the request defines the protected virtual machine and the port policies applied to it. For each port, you specify the port number, protocol, approved source address ranges, and maximum request duration. For example, you might protect SSH on port 22, allow requests only from your corporate public IP range, and limit each request to 3 hours. The duration uses the ISO 8T601 format. A value such as PT3H represents a 3-hour access window. Do not leave the permitted source range unrestricted. A JIT request that temporarily allows the entire internet defeats much of the benefit. Also remember that configuring a JIT policy and requesting JIT access are separate operations. The policy defines what may be requested. A later request temporarily activates access for a specific source address and time window. Because Azure API versions and request formats can change, validate the final REST command against the current Microsoft documentation before using it in production automation. Let's configure JIT through the Azure Portal. Open Microsoft Defender for Cloud and locate just-in-time VM access. Depending on the current portal layout, you may find it under Workload Protections or by searching directly for just-in-time VM access. Select the virtual machine you want to protect and configure the management ports that administrators are permitted to request. For a Linux VM, that will commonly include SSH on port 22. For a Windows VM, it may include RDP on port 3389. For each port, choose the protocol, allowed source address ranges, and maximum access duration. Use a specific corporate CIDR range or the requester's current public IP address rather than allowing every internet address. Save the policy. When an administrator needs to connect, the administrator submits a separate access request. Defender for Cloud temporarily permits the approved source address for the selected duration. When that duration ends, access is removed automatically. Before relying on the configuration, review the VM's effective NSG rules. An existing higher priority rule that already allows SSH or RDP from the Internet can undermine the protection JIT is intended to provide. One more quick checkpoint to lock that in. We've set up JIT with a 3-hour window. What actually happens on the wire when the clock runs out? Take a second. Picture a developer who accidentally commits a private SSH key to a public code repository. JIT still provides an important layer of protection. If port 22 is closed to the attacker's source address, possession of the key alone does not make the VM reachable. But the credential remains compromised. If SSH is later opened to a broad source range, if the attacker gains access through another machine on the network, or if another path to the VM exists, the stolen key may still be used. That is why network controls and identity controls must work together. JIT reduces when and from where a management service can be reached. Microsoft Entra authentication reduces dependence on long-lived user passwords and unmanaged SSH keys. With Microsoft Entra ID, administrators authenticate using centrally controlled identities. Access can be granted or removed through Azure RBAC. Authentication can be governed through supported conditional access scenarios, and the SSH process can use short-lived certificates instead of permanent user key files. Here's how Microsoft Entra authentication works for a supported Linux VM. First, the VM has a system-assigned managed identity enabled. Second, the A-login for Linux extension is installed on the VM. Third, the user receives either the virtual machine user login role for standard access or the virtual machine administrator login role for administrative access. When the user connects through a supported method, such as the Azure CLI command AZSSHVM, the user authenticates to Microsoft Entra ID. Microsoft Entra authentication is then used to obtain a short-lived Open SSH certificate. The certificate identifies the user and is valid only for a limited period. The VM's Entra login components validate that certificate and verify that the user has an appropriate Azure RBAC login role. If both checks succeed, the VM creates the Linux session. This gives you centrally managed identity access without distributing permanent user SSH private keys to every administrator. Let's look at the main configuration steps. For a Linux VM, first enable the system-assigned managed identity. The Entra login extension depends on this identity, so do not skip this step. Next, install the login for Linux extension. The extension publisher is Microsoft Azure .Active Directory. Then assign the appropriate Azure RBAC role to the user or group. Use virtual machine user login when the person needs a standard Linux session. Use virtual machine administrator login when the person requires administrative access. Assign the role at the narrowest reasonable scope. A role assigned directly to one VM grants access only to that VM. A role assigned at the resource group or subscription level can grant access to multiple VMs within that scope. After configuration, test the login using a supported client such as Azure CLI with AZSSH VM. Remember that an Azure management role, such as reader or contributor, does not automatically grant operating system login rights. The user must receive one of the dedicated virtual machine login roles. Now let's connect to the VM. If JIT protects port 22, request JIT access first and restrict the request to your current public IP address. Then use a supported connection method. From Azure CLI, you can use AZ/SSH VM and specify the VM name and resource group. If your Azure CLI session is not already authenticated, Microsoft Entra ID prompts you to sign in. After authentication, the SSH integration obtains a short-lived OpenSSH certificate and uses it to connect to the VM. You can also use Azure Bastion for a browser-based connection when Bastion and the VM are configured for the supported Microsoft Entra authentication experience. The exact interface depends on the connection method. Azure CLI, Azure Bastion, and other supported clients do not all display the same screens. The important point is that access is tied to the user's Microsoft Entra identity and Azure RBAC role rather than a shared local password or a permanent user key copied between machines. Here are several problems that commonly prevent Microsoft Entra VM login from working. First, confirm that the VM has a system-assigned managed identity enabled. Second, verify that the AAD/SSH login for Linux or AAD login for Windows extension is installed successfully and reports a healthy provisioning state. Third, confirm that the user has either the virtual machine user login role or the virtual machine administrator login role at the VM resource group or subscription scope. Fourth, verify that the VM can reach the Microsoft identity and management endpoints required by the login extension. Strict outbound firewall rules or broken DNS resolution can interrupt authentication. Fifth, use a supported login method, a traditional SSH command that explicitly uses an old private key is still performing key-based authentication. It does not automatically become Microsoft Entra authentication. Finally, separate user login from workload identity. The VM's system-assigned managed identity is required as part of the Entra login configuration. Applications running inside the VM can also use managed identity to access resources such as Key Vault or storage. But those application permissions are separate from a human administrator's VM login permissions. Recall from Part 2, you attached a 400,000 IOPS Ultra disk to a small VM, yet your application only sees a few thousand IOPS. Why? Because the VM size itself imposes a maximum uncached disk IOPS and throughput cap. The VM throttles all attached disks. This matters now because encryption can add performance overhead, and you don't want to hit an IOPS wall while securing your data. A financial organization enters a security audit believing that its Azure-managed disks are unencrypted. That is not the actual problem. Azure-managed disks are encrypted at rest by default using server-side encryption with platform-managed keys. The organization's data is not sitting unencrypted on physical storage. The audit finding is more specific. The organization's internal policy requires it to control key rotation, key expiration, key revocation, and separation of duties. The default platform-managed key does not satisfy that requirement. The organization therefore needs to evaluate customer-managed keys through a disk encryption set, and possibly encryption at host if it also needs protection for temporary disks and disk caches. This distinction matters. The question is not simply, is the disk encrypted? The better questions are, which parts of the storage path are protected? Who controls the keys? And what compliance or operational requirement are we trying to satisfy? Azure VM encryption is not a choice between only two products. There are several layers, and each one protects something different. First, Azure managed disks use server-side encryption with platform-managed keys by default. Azure manages the encryption keys for you. Second, server-side encryption with customer-managed keys lets your organization control the key in Azure Key Vault or a supported managed HSM. A disk encryption set connects that key to the managed disks. Third, encryption at host extends encryption protection to areas such as temporary disks and the caches associated with OS and data disks. It operates beneath the guest operating system and does not require BitLocker or dmcrypt extensions inside the VM. Fourth, Azure Disk Encryption uses BitLocker on Windows or dmcrypt on Linux inside the guest operating system. However, Azure Disk Encryption is now a legacy path. Microsoft has scheduled ADE for retirement on September 15, 2028. For new architectures, evaluate server-side encryption, customer-managed keys when required, and encryption at host. Existing ADE workloads should have a documented migration plan well before the retirement date. Azure Disk Encryption, or ADE, performs encryption inside the guest operating system. On Windows, it uses BitLocker. On Linux, it uses dmcrypt. The Azure VM agent and disk encryption extension participate in configuring and reporting the encryption process. Azure Key Vault stores or protects the encryption secrets needed by the deployment. When a key encryption key is configured, it adds another wrapping layer around the encryption material. This design creates several dependencies. The VM agent must be healthy. The extension must install successfully. The operating system and disk layout must be supported. DNS and network connectivity must allow the VM to reach required Azure and Key Vault endpoints. Key Vault permissions and protections must also be configured correctly. If any part of that chain fails, encryption may not complete or an encrypted disk may not unlock as expected. This complexity is one reason Microsoft is retiring ADE and directing customers toward newer encryption approaches. Because Azure Disk Encryption is scheduled for retirement, this lesson will not treat ADE as the default choice for new virtual machines. You may still encounter ADE in an existing environment, so your first task is discovery. Identify which VMs currently use ADE. Record their operating systems, disk configurations, Key Vault dependencies, recovery procedures, and business owners. Then review Microsoft's current ADE migration guidance. Migration is not always a simple matter of turning off one setting and enabling another. The supported process can vary by operating system, disk layout, encryption state, and target encryption method. Test the migration on a non-production copy of the workload. Confirm that the VM can restart successfully, applications can access their data, backups remain recoverable, and your operational team understands the new key dependencies. The most important command is not a single PowerShell cmdlet. It is a controlled migration plan completed before September 15, 2028. When an ADE extension fails, avoid guessing and repeatedly rebooting the VM. Start with the dependencies. Confirm that the Azure VM agent is running and healthy. Check the disk encryption extension status and review its detailed error message. Verify that the operating system, disk layout, and encryption scenario are supported. Confirm DNS resolution and outbound connectivity to the Azure and Key Vault endpoints required by the deployment. Review the Key Vault configuration. ADE requires the necessary Key Vault permissions and protections, and older deployments may use configurations that differ from newer RBAC-based designs. Check whether endpoint security software, group policy, an existing BitLocker policy, or another encryption product conflicts with ADE. Also review the platform logs before removing or reinstalling the extension. Making changes without understanding the current encryption state can place the VM at risk. Finally, remember the larger objective. Because ADE is retiring, repeated failures may be a sign that you should prioritize migration rather than investing more time in expanding a legacy architecture. Quick recall check. Azure Disk Encryption is scheduled for retirement on what date? The answer is September 15, 2028. Existing ADE workloads need a tested migration plan before that date. This is not something to leave until the final month, because encryption migrations require validation, restart testing, backup testing, and coordination with application owners. For modern Azure VM deployments, start by understanding the requirement. If the organization needs control over the key used to encrypt managed disks, use server-side encryption with a customer-managed key. You create a key in Azure Key Vault or a supported managed HASM. Then you create a disk encryption set. The disk encryption set uses its managed identity to access the key and connects that key to the managed disk. The encryption occurs at the Azure storage layer outside the guest operating system. If the requirement also includes temporary disks and host-level disk caches, evaluate encryption at host. These controls can be used to address different layers. Customer-managed keys give the organization control over managed disk encryption keys. Encryption at host expands protection to host-side storage paths that ordinary managed disk encryption does not fully cover. The correct design may use one or both, depending on compliance, workload support, performance, recovery, and operational requirements. Let's create the customer-managed key architecture. First, create or select an Azure Key Vault in the appropriate region and subscription design. Enable soft delete and purge protection. These controls reduce the risk that someone accidentally or maliciously deletes a key that active disks still require. Create a supported encryption key and document its rotation and recovery procedures. Next, create a disk encryption set. During creation, select the customer-managed key. The disk encryption set receives a managed identity. Grant that identity the key vault permissions required to use the key for disk encryption. After the disk encryption set is ready, associate it with supported OS and data disks. Before changing a production disk, confirm that the disk type, VM configuration, region, and intended encryption combinations support the operation. Some changes can occur while a VM remains online, while other scenarios may require deallocation, recreation, or a different migration procedure. Do not promise zero downtime until you validate the exact workload. Finally, test key rotation and recovery. Customer-managed keys provide greater control, but they also create greater responsibility. If the key or its permissions become unavailable, protected disks may become inaccessible. A quick throwback to Part 1. Which VM series did we say was designed specifically for high disk throughput? This becomes important if you're running disk encryption. You don't want your IOPS capped by the wrong size. Picture a company that has implemented several strong controls. JIT restricts the management ports. Microsoft Entra ID controls administrator login. Managed disks use an approved encryption design. But a public-facing application running on one VM still contains a critical vulnerability. The attacker does not need RDP or SSH. The attacker exploits the application directly. This is where workload protection and continuous detection become essential. Defender for servers can combine security recommendations, endpoint detection and response, vulnerability assessment, agentless machine scanning, and additional server protection capabilities depending on the selected plan and configuration. The security team can use those findings to identify vulnerable software, investigate suspicious activity, understand exposure, and choose the correct remediation path. Defense in depth does not assume that every preventive control will succeed. It provides additional opportunities to detect, contain, and recover when one layer is bypassed. Defender for Servers Plan 2 is the more comprehensive server protection plan in Microsoft Defender for Cloud. It can provide advanced workload protection capabilities for supported Azure VMs, Azure Arc-enabled servers, and connected multi-cloud machines. Major capabilities include integration with Microsoft Defender for endpoint detection and response, vulnerability assessment through Microsoft Defender Vulnerability Management, just-in-time VM access, and agentless machine scanning. Agentless scanning can inspect supported machines for software inventory, vulnerabilities, secrets, and malware without installing a separate scanning agent on each machine. Additional capabilities, such as file integrity monitoring and other workload protection features, depend on the current product configuration, supported operating systems, and enabled components. Plan features can change over time, so confirm the current Microsoft plan comparison before recording the on-screen pricing or feature table. The important architectural distinction is that Plan 2 provides the broader set of advanced server security capabilities, including JIT and agentless machine scanning. To enable Defender for Servers Plan 2, open Microsoft Defender for Cloud and go to Environment Settings. Select the subscription or connected environment you want to protect. Open the Defender plan's configuration and enable Defender for Servers Plan 2. Then review the plan's individual settings and extensions. Confirm that Microsoft Defender for Endpoint Integration is configured as required for your supported servers. Review the Vulnerability Assessment configuration. Current integrated vulnerability scanning uses Microsoft Defender Vulnerability Management and can provide agent-based and agentless assessment depending on the plan and machine configuration. Review agentless scanning and confirm that it is enabled where appropriate. Do not assume that Azure Monitor Agent or a specific log analytics workspace is universally required for every Defender for Servers feature. Logging and monitoring agents may still be required for separate data collection scenarios, but Defender for Endpoint and agentless scanning use their own architectures. After enabling the plan, allow time for supported machines to appear and complete their initial assessments. Then review coverage, recommendations, and any machines that have not onboarded correctly. Inside Defender for Cloud, open the Recommendations page and locate the Vulnerability Assessment recommendations for machines. Select an affected VM and review the findings from Microsoft Defender Vulnerability Management. For each finding, examine the severity, affected software, available remediation, known exploit information, internet exposure, and business importance of the machine. Do not treat every vulnerability as an operating system patch. A Windows or Linux operating system vulnerability may be remediated through Azure Update Manager. A vulnerable Java library, web framework, database engine, container image, or custom application may require an application upgrade, package update, new deployment, or vendor-specific procedure. Create a remediation plan using the tool that owns the affected software. That might be Azure Update Manager, Microsoft Intune, Configuration Manager, Ansible, a CI/CD pipeline, an image building pipeline, or a manual vendor upgrade. After remediation, rescan or wait for the next assessment cycle and confirm that the finding clears. Defender for Cloud helps you discover and prioritize the risk. It does not automatically guarantee that one remediation button can safely patch every type of vulnerable software. Let's lock in one important distinction. Which Defender for Servers plan provides the broader advanced feature set, including just-in-time VM access and agentless machine scanning? The answer is Plan 2. Also remember that vulnerability assessment is not the same thing as patch deployment. Assessment finds and prioritizes vulnerable software. Azure Update Manager, or another operational tool, performs the appropriate update when a supported patch is available. Before deploying another security extension, understand the difference between anti-malware and endpoint detection and response. Microsoft Anti-Malware for Azure can configure malware protection on supported Windows virtual machines. It can enable capabilities such as real-time protection, scheduled scans, exclusions, and signature updates. Microsoft Defender for Endpoint provides a broader enterprise security platform. It includes behavioral detection, endpoint detection and response, alert investigation, threat hunting, and response capabilities. Defender for Servers can integrate protected servers with Defender for Endpoint depending on the selected plan and onboarding configuration. These tools are related, but they are not interchangeable. Before deploying the Microsoft Anti-Malware extension, check whether the server is already protected by Microsoft Defender Antivirus and onboarded to Microsoft Defender for Endpoint. Avoid creating conflicting policies or assuming that installing one extension automatically provides the full Defender for Endpoint experience. Use policy-based deployment at scale and verify protection status from both the operating system and the appropriate Microsoft security portal. A server can have strong network security, secure administrator authentication, encrypted disks, and endpoint detection, and still be compromised through an unpatched application. The proxy logon vulnerabilities disclosed in 2021 demonstrated the danger. Internet-facing Exchange servers required urgent, workload-specific remediation. But patching a complex enterprise application is not always the same as installing an ordinary operating system update. Exchange server, database platforms, identity systems, and other critical workloads may require prerequisite checks, maintenance mode, service sequencing, health validation, backups, and rollback planning. The lesson is not to click Install Everything without understanding the workload. The lesson is to maintain an accurate inventory, monitor security advisories, prioritize actively exploited vulnerabilities, automate routine updates where appropriate, and use application-specific procedures for complex systems. Automated patch management is essential, but safe patch management is both automated and workload-aware. Open Azure Update Manager in the Azure Portal. From the Overview page, review the update compliance status of your Azure VMs and Azure Arc-enabled servers. To schedule recurring patching, create a maintenance configuration with the guest maintenance scope. Choose the operating system patch classifications you want to deploy, such as critical and security updates. Define the recurrence, time zone, maintenance window, reboot behavior, and any update exclusions required by the workload. Next, assign the maintenance configuration to specific machines or create a dynamic scope. Dynamic scopes can select machines using properties such as subscription, resource group, region, operating system type, resource type, and tags. Azure evaluates the dynamic criteria when the schedule runs, so newly created machines that match the scope can be included automatically. Use tags carefully. For example, you might define patch rings such as Pilot, Production 1, and Production 2, rather than patching every production server simultaneously. After each maintenance window, review deployment results, failed installations, reboot status, and machines that were not assessed. For a larger environment, define Azure Update Manager maintenance configurations through Azure, CLI, PowerShell, Bicep, Terraform, or another controlled deployment process. Your automation should define more than a weekly recurrence. Specify the guest maintenance scope, time zone, maintenance window, patch classifications, reboot behavior, and resource assignments. Use dynamic scopes or policy-driven assignments to include machines based on consistent tags and environment standards. Create a pilot ring first. Patch a small group of representative non-production machines, monitor the results, and then proceed to broader production rings. Also account for workload dependencies. Do not reboot every domain controller, cluster node, application server, or availability set member at the same time. Coordinate sequencing for highly available and stateful systems. Azure Update Manager provides centralized assessment and deployment, but your architecture must still define testing, approvals, maintenance windows, rollback procedures, exception handling, and post-patch validation. Always verify the current Azure CLI or infrastructure as code parameters against Microsoft's latest documentation before using the commands in production. That's defense in depth for Azure virtual machines. Start with the network. Remove unnecessary public IP addresses, restrict NSG rules, use Azure Bastion or private connectivity where appropriate, and protect management ports with just-in-time access. Then secure administrator identity. Use Microsoft Entra authentication for supported VM scenarios. Assign virtual machine user login or virtual machine administrator login at the narrowest practical scope, and avoid shared local credentials. Next, choose the correct encryption architecture. Remember that managed disks are encrypted at rest by default. Use customer-managed keys when your organization must control the encryption key. Evaluate encryption at host when you need additional protection for temporary disks and disk caches. If you still operate Azure Disk Encryption, begin planning its migration before the September 15, 2028 retirement date. Finally, enable continuous protection. Use Defender for servers, Microsoft Defender Vulnerability Management, Endpoint Detection and Response, Anti-Malware Protection, and Azure Update Manager to identify and remediate risks before they become incidents. No single control makes a VM secure. The strength comes from multiple independent layers working together. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.